We are all familiar with the concept of rate of change. Speed or velocity is simply change in distance traveled divided by time elapsed, or change in distance traveled divided by change in time. Notice there are two quantities that are changing. First is the time and the second distance traveled. Velocity is amount of change in distance for one unit change in time. The time changes by 1 unit. How much has the distance traveled changed? This is known as rate of change of distance with respect to time. Notice this with respect to. The rate of change of some quantity can also be with respect to something other than time. The denominator here need not always be time. Let me explain. It is known that area of a circle is Pi.r-square. Pi is approximately 3.14 or 22 by 7. It is also common to retain the pi symbol in most calculations instead of writing its numeric value, and substitute the value of pi only when the numeric value is required. The area of the circle depends on the radius. Hence, it can be said that area is a function of radius. I create a circle with radius, say 3 centimeters. It has an area of Pi.r-square, which works out to 9 pi or approximately 28.26 centimeters square. I have some way to expand the circle, retaining its shape, and so I expand the radius to 4 centimeters. The area now becomes pi into 4 square, approximately 50.24 centimeter. Notice here two quantities are changing, the radius and the area. What is rate of change of area with respect to radius? This is equal to change in area divided by change in radius. Change in area, the shaded region, divided by change in radius. 21.98 square centimeter per centimeter. This square centimeter is the change in area, and this per centimeter is the change in radius. Hence the unit 21.98 square centimeter per centimeter. Notice this is the average rate of change of area of a circle with respect to radius, for radius changing from 3 centimeter to 4 centimeter. We had a similar situation in the limit part 1 lesson, where we had calculated average speed of the stone, which was nothing but average rate of change of distance for time changing from 3 seconds to 4 seconds. Also note that this average rate of change of area with respect to radius, if calculated for change of radius from 3 centimeters to 3.5 centimeters, will give a different result than above. Change in area divided by change in radius. This works out to 20.41 square centimeter per centimeter, as against the previous number calculated as 21.98 square centimeter per centimeter. As is obvious, This again is average rate of change of area. Now, how do we find out the instantaneous rate of change of area with respect to radius? Instantaneous here does not refer to the same instant of time, it refers to the same value of radius. Now we are talking of rate of change of area while radius changes. At the same time, we are saying it should not be average from one value to another value. Value of radius should remain instantaneous, or I can say value of radius should remain fixed at what it was. So this is what is called limit of rate of change of area with respect to radius while the change in radius approaches 0. We had a similar situation in the instantaneous velocity where we had defined instantaneous velocity as the limit of average rate of change of distance for a period of delta t, and then take the limit of that as delta t approaches 0. So the trick here is take the average rate for some finite amount of delta t, finite would here mean non-zero, and then take a limit of that with delta t 0. This was the case for instantaneous velocity. So in the case of rate of change of area, I would use the similar technique. Take the average rate of change of area for a change of radius of delta r, and then take the limit of that as delta r tends to 0. Let us attempt to calculate it like we did for instantaneous velocity in earlier lesson. Initial radius is equal to r, initial area is pi r square. Final radius is equal to r plus delta r. So radius changes from r to r plus delta r, and we will calculate the average rate of change of area for a change of radius of delta r amount. Final area works out to pi into r plus delta r whole square is equal to pi r square plus 2r delta r plus delta r square. Rate of change of area with respect to radius is equal to final area minus initial area, that is the change in area, divided by final radius minus initial radius. Final area minus initial area divided by final radius minus initial radius. Now this is average rate of change of area. To find out the instantaneous rate of change, we will take the limit of this as delta r tends to 0. Delta r approaches 0, but it is not exactly 0. So we can cancel out this delta r, and we get. Now if I take a limit on both sides, limit as delta r approaches 0 of average rate of change is limit as delta r approaches 0 of this expression. As delta r approaches 0, this portion will become smaller and smaller, and in the limiting case we will be left with. So instantaneous rate of change, instantaneous here has to be taken with a pinch of salt. This instantaneous does not actually refer to the same instant in time. it refers to delta r approaching 0, that is the rate of change while r remains almost constant, very close to constant, limit of r just not changing. Congratulations, you have just found what is known as the derivative of area with respect to radius. This instantaneous rate of change of function fx, area is a function of r, which is pi r square. Instantaneous rate of change of a function fx with respect to x is called derivative of fx with respect to x. So what we have found out is derivative of fr with respect to r. It is also known as differential coefficient of fx with respect to x. Mathematical language written as d by dx of fx and often simply denoted as f dash x. Here we can have a function of r, fr. So we are talking of d by dr of fr, which was 2 pi r, or we can say f dash r. So this is the concept of differential coefficient or derivative, which essentially is instantaneous rate of change of the function with respect to the variable of the function.